Okay, so now we're going to start talking about capacitors. I like starting, and capacitance. I like starting this unit with a dramatic demonstration of a capacitor. Let me just, up until now, we've been talking about, this isn't the first time I've talked about capacitors. Up until now, I have talked several times about conducting sheets or charged sheets, areas that are charged. And so let's say I charge this plate up with a positive charge. And then I take another plate and I put it close to it. And I charge that guy with negative charge. I now have a capacitor. Okay. How do I set this kind of a system up? Well, I could just take two uncharged plates, put them close to each other, and then connect them to a battery. And battery, the symbol for battery is that guy. If there's multiple battery cells and you get a couple of them, that's the schematic symbol for a battery. So here's a battery with the positive terminal here and the negative terminal there. If I take two uncharged plates and then just connect them, then I create, it's an open circuit, so it's not going to keep flowing forever. But initially, the negative charges in the negative terminal of the battery, the electrons, move onto this plate. And as they move onto that plate, they repel negative charges from that plate. And so just by taking two conducting plates, sticking them close together, and then sticking each plate to the opposite terminal of a battery, you create a capacitor. You create a separation of charge. And I can show you that here. This isn't a dramatic demonstration, but I can show you that here. Wrong way. So I don't know if you'll be able to see this. Here I go. Here I got a circuit board. It's got a light bulb and a switch, two batteries, two D-cell batteries, and a capacitor. This is a demonstration capacitor. It's large, just so you can show it. Obviously, this capacitor does not look like two parallel plates, but I've talked about this before. To maximize the capacitance, one of the things you can do is just increase the area. And so you can get a very large area capacitor. You can have plates with very large areas into a relatively small space just by rolling them up, right? So you get two conducting sheets and you stick what's called a dielectric in them. That's just something to separate them, something that we'll talk about in a little bit. Couple days, and then you just roll it up into a tube. So this is still a parallel plate capacitor. Anytime you see these, like the one that I showed you from my pool pump, which I can't locate now. It's okay, it's a bad one. Okay, it's right in front of my face. Yeah, this one that's from my pool pump, that's one. This little black one that's from camera flashes, right, old school cameras, disposable cameras, they need a capacitor in there. Because the battery can't provide a big flash all at once. But the battery can slowly load a capacitor, and then that capacitor can rapidly discharge. But anyway, so this capacitor is initially uncharged. Once I close the switch, exactly what I explained up here is going to happen. The electrons are going to travel from the negative terminals of the batteries, load onto one plate. They're going to drive by the Coulomb force. They're going to drive the electrons off of the other plate. And so you're going to get a flow of electricity until you get so much charge built up on this that it's no longer going to flow, right? Because the more negative charge you build up on this plate here, the more these charges are going to repel any more incoming charges, right? Does that make sense? And then it will stop. And so I can see the process happening by, I put it in quotes. I can see that process happening by inserting a light bulb here. Because if charges are flowing through the circuit, the light bulb will light up. And so when I close the switch, sure enough, it lights up, but then it slowly dims. Because as time progresses, more and more negative charges more and more electrons get built up on the negative plate, and so they fight more incoming negative charges. Initially, there's no resistance to the electrons, so the light's brightest right at the beginning, and then it slowly dims as the capacitor is charging. Now I have charged capacitor. Now I can take Now I don't have a battery in here anymore. I just have the capacitor and the light bulb. Now the exact opposite's going to happen. Oops. Oh, did I already discharge it? Now if I remove this battery and put a light bulb in there, once I connect that circuit, all the electrons in this guy, they're feeling repulsion from each other, and so they're going to flow through the circuit. And so they can get to the positive, right? They're attracted to the positive terminal, but they're not allowed to go this way, so they're going to go that way. And when they do that, you get the light bulb lighting up. And now the capacitor is discharging, okay? So the electrons are flowing. So that's how you can see this happen. Yeah?
Would an electric lighter use a capacitor?
I don't know. I don't think so.
Maybe you just run on a powerful battery.
What do you mean electric lighter?
It's a lighter, but it almost looks like plasma in between.
Oh, I know what you're talking about. I don't know. I don't know how those work. I would say bring one to school and we'll take it apart, but you probably shouldn't.
I don't have one.
Okay. All right, so that's the basic construction of a capacitor. The first capacitor was something called a Leyden jar. Some people will say Leyden jar, but the teacher I first learned this from said, "Oh, it's sitting right in front of my face already." It's this guy. This is the first way that people ever figured out how to store electric charge. And again, this is back in Ben Franklin's day. Yeah. Oh gosh, thank you. This is too much. Too much.
Sounds like you haven't been here for a week.
No way.
I was actually here yesterday.
Maybe you're here all week. Yeah.
Oh yeah, because I live here. So this is a Leyden jar, named after the place that it was actually first conceived. I think it was in England. I don't know, somewhere. But all it is a jar, hence the name, that has a metallic paint on the inside. So you have a metallic coat of paint on the inside, and then another metallic coat of paint on the outside. So essentially you have two conductors that are then separated. And so if you charge one and provide a conducting path for the electrons to leave another one, you can build up charge, just like in a normal capacitor. And then the lid, how do you access the inner plate? Well, that's what the ball on the post is for. It's a conducting ball, conducting post, and then a metal chain that then makes contact with the inner plate. So that's like all the inner plate, the inner capacitor plate, and this is the outer one, separated by glass. And what you'll see, what we'll learn about when we study dielectrics very soon, is that by putting plastic or glass or paper or some other type of material between the capacitor plates, you actually can control the amount of energy you can store. You can control the electric potential difference between the capacitor plates. You can control the amount of charge that you can store on the capacitor plates by changing the material that you actually put in between them. But that's a little bit in the future here. But anyway, now what I can do, and what I'll do in a second, is I can make contact with this guy on the Van de Graaff generator. This is my Van de Graaff. That's the Van de Graaff generator. Van de Graaff generator builds up positive charge. Right? This particular one, most do. The dome builds up positive charge. And so as this guy builds up positive charge, he's going to pull electrons off of the inner plate, right? It's going to pull electrons off of the inner plate via the path through the chain, through the post, and through the ball up there. So the electrons are going to leave that, leaving a net positive charge on the inner plate, right? You with me? Now, as that happens, if I connect the outer plate to the ground via a ground wire, and the schematic for a ground wire is 3 lines, they get progressively skinnier or shorter.
Tornado.
Or looks like a tornado, yes. If I provide a ground wire, well, now as the inner plate becomes positively charged, the outer plate, you're attracting electrons, right? It's trying to pull electrons onto the outer plate because they're attracted to the positively charged inner plate. And so you can pull those electrons from the ground as long as it's grounded. If it's not grounded, then you can't do that. You're just going to separate the charges within the outer plate itself. But then you build up this negative charge here. Now, obviously, if you have positive and negative, there's electric potential here, there's electric potential here. There's a positive electric potential here, there's a negative electric potential here. There is a potential difference between the two plates, right? So any capacitor that is charged, there's most definitely going to be a potential difference, a delta V, across the two plates. And so this, again, this is the first capacitor. This is the first way that people devise to actually store electric charge. And I've read stories about how, like, the scientists like Ben Franklin and his ilk, they would have their assistants come in the morning and get on exercise bikes and, like, just ride the bikes to build up the friction. And they would charge up a bunch of these, like, in the morning, and then they would come in and do their experiments on them. I don't know if you guys noticed, it's been very dry the last week because of the weather. Have you noticed the static?
Yeah.
Like in your blankets and your clothes and just what? It's been crazy static.
It was I got a huge, like, static.
Yeah, I've been shocking my dogs and my wife like a ton.
Basically, whenever I would be wearing jeans on the couch, and I would get up, I would have to, like, touch the corner of the wall with the little metal plate.
Otherwise, you're gonna shock yourself. Yeah, and it's because it's so dry. And I think we talked about it before. The water molecules actually will flow over things because they are polar. It's mostly water molecules. The polar water molecules will kind of borrow the electrons and redeposit them to help dissipate charge. But when it's real dry, static electricity, it's a lot more noticeable. Okay, anyway. So there's electric potential difference between these guys. Notice, though, there's no path. There's no path that the electricity can flow from one plate to the other. Okay. What's cool about these is that I can charge that up, and it does work on dry days. I tried it first period, and it worked. I can charge this guy up so much that it actually forces the air to become a conductor. And then you can get a real big... Once the potential difference between the inner plate and the outer plate is so high, it's not going to be able to flow through the glass. It's a very good insulator. But it can flow through the air. It can force the air to become a conductor, just like lightning does. Just like the little sparks do whenever you've been getting shocks. And so you can get a real large spark going from the outer one, going from the one of the plates to the other plate. But if I don't do that, then I can just store energy in this guy. And so let me do that real quick. I'm not going to go so far that it will actually end up sparking yet, but notice I got to have this ground wire, otherwise it's not going to work. So if I just do this, it's not going to work. I have to ground the outside. Now it's charging. Now it's got some charge on it. It's probably got enough charge on it to really give you a jolt. Much more than the Van de Graaff generator by itself would. Forgot about the video again. Let's bring it up here. People at home, I'll show you what I just did in a second. So can everyone see that? So now with this guy, I can connect the outer plate and the inner plate and actually discharge it. Oh, that wasn't that much. Let's do that one more time.
Did you ground it whenever you're touching it, or?
Not really, no. A little bit, but there's a lot of charge on this, and it takes time to flow. You can get a lot more charge for reasons that we'll talk about. You can get a lot more charge on this than I can on this. That's why this I'm very careful with whenever
You should move the camera if you're going to do it again.
Oh gosh.
Just keep the remote on you at all times.
Oh no, how do I strap your belt or something?
Oh, this would be good thing we have the capacitor.
Charge the camera. Maybe they can see it directly without.
All right. Play it again, Sam. Let it charge for a little bit now. Did you notice that it took much longer for this guy to start sticking up into the air whenever I was charging the capacitor plate, or the capacitor? That's because all the charge that normally would have just accumulated immediately and made it shoot up was now loaded onto the capacitor. Oh my gosh. So here, now I have the charged capacitor. Again, if I was to touch both, then I would complete the circuit and it would flow through me, and I'm not going to do that. But if I just do it like, that still isn't that much. And then there's residual charge. For reasons that we'll learn about, there's still electrical energy stored in this guy that dissipates over time. And so it'll still give you a little jolt. Now what's fun though is if you overcharge it, you can actually get a spark going from the inner pole there to the outer plate. And I'm going to let Gianni do that. I actually shocked myself doing this one of my first years teaching because I had my hand too far up, and so it actually went through my hand, and I blacked out for a second, and like I didn't fall, but like I didn't know what happened, and then my students were all kind of giggling and laughing at me. But yeah, so I hold it down below. It takes a little bit. Come on. There we go. So notice that spark is significantly bigger than any spark that you get off this guy. This guy is never afraid to touch. Oh, that's still pretty big. Wow. Woo. Jeez. See, it's very dry. Static electricity works very good on dry days. See, and there's still energy there. Still energy there. So this guy, as you can plainly see, can hold a lot more charge than this guy. Which is to say this guy has a lot more capacitance than this guy. Okay. Yes.
What would happen if you were to stick that outside plate on the ground generator and then ground the little...
Oh, same thing.
Okay.
You get the same effect.
Okay.
I've never done it like that. I think it's just easier to do it the other way.
Probably.
Yeah. That's a good question, though. My first few years, and I stopped doing this for a specific reason, but my first few years teaching this, I would actually charge up the Leyden jar, and then hold it on one side, and then have a ring of students all hold hands, and then the person on the other side would then touch it. But the last time I did that, there were students complaining like 3 and 4 days later that their arms were still sore. So I stopped doing that. Anyway. Okay.
Also COVID.
Yeah.
Oh yeah, that too. I stopped doing that long before COVID though, because I didn't want. I was scared. I was like, oh,
You're just a strong predictor.
Yeah, I think someone with like a pacemaker or something like to their car.
well, I made sure. You probably don't want to voluntarily have electricity pass through your body when you have a pacemaker.
You should just sign a waiver. Jury and executioner, Mr. Gray.
Okay.
You've been sentenced to death because you have a pacemaker.
Okay. So let's say we have 2 capacitor plates that are charged. I'm just going to draw them as lines here. And we're going to assume their areal extent is much, much larger than the distance that separates them. So imagine these guys going off to infinity, right? So that the distance that separates them, d, is much, much smaller than the actual area of the plates. And let's say that the top guy has positive charge. And we know, make sure everything is, we know that the charge density, the area charge density, is just the total charge divided by the area. And so we can talk about the actual total amount of charge stored on that conducting sheet. Is just going to be whatever the charge density is times the area, right? By this equation here. So I can say that this guy, let's say he's the positive one, so that charge on the top plate will be positive, and it's just sigma times the area. And if I've charged this setup using a battery, then I'm going to get the negative amount of charge on the other side. The charge density will be the same, it's just going to be the opposite charge. Again, because that's just what happens, right? When one capacitor plate gets loaded up with negative charges, it drives an equal amount of negative charges off of the other capacitor plate, creating an equal magnitude charge on the opposite plate. And then because we have positive charge here and negative charge here, we know the electric field is going to be pointing from positive to negative. Okay. What do you think the electric field is here? Or here? Are you sure about that?
Wait, outside?
Outside.
Oh, outside.
Remember, consider that these are infinitely long.
Okay, that's
We were all just thinking.
I was like,
I wanted to say 0, but I was like, is it?
Well, let's look at why. Remember, and someone said, the electric field due to a single charged conducting plate, or charged plate, is going to be sigma over 2 epsilon naught, right? The electric field in here is the electric field due to the positive plus the electric field due to the negative. They both point in the same direction, so this guy is just sigma over epsilon naught, right? But up here, you have the electric field lines pointing away from the top plate, but the electric fields due to the bottom plate up above are going to point in the opposite direction.
And since the area is infinite, the distance away doesn't matter.
Exactly. Yeah. And not only that, but yeah. Since the area is infinite, or close enough to be considered thus, then this guy is going to be, it's not dependent on distance. Exactly. And so the same thing happens down here. And so for capacitors, and this is one of the many ways that capacitors just make the hardcore mathematics of electric potential and electric potential difference a lot easier, because it's like, well, it just simplifies, right? Just like inside here, we can do the integral, the negative integral of E dot dr, but it's just going to end up being E times the displacement, the electric field times the displacement, because the electric field in here is constant, so the integral becomes easy, right? Let me just remind you of that, since it has been years since we've met and discussed this stuff. So we'll kind of ease our way into it. Let's say I want to calculate the potential difference between these two plates. Well, it's the negative integral from where you start. And so let's call this plate A and this plate B, from A to B of the electric field dotted with the displacement directions, right? The incremental displacement as we do our integral. Well, if we're going from A to B, the electric field points down, and when I integrate from A to B, every dr is going to be pointing down. So E dot dr, the angle between them 0, so it's just going to be E times, well, it's going to be E times dr. The dot product gives you the scalar E dr times the cosine of the angle between them. The angle between them is 0 degrees, so it's 1. So it's just going to be E times dr. So this integral becomes, this is a good exercise. This is a good thing to do to just refresh what we were talking about before the break. Before the impromptu break. We get the negative integral from A to B of E dr. But because we're dealing with infinite plates of charge, the electric field is constant. Okay? And even in real capacitors, the electric field is constant between the plates until you get to the edges. The edges, there's things called edge effects, and there's simple ways to, more complex than we deal with in this class, but there's ways that you can deal with those that aren't too terribly difficult. But for the most part, the area of interest is the vast space that is between the edges. And so the electric field is constant there, so you can just pull that out of the integral. So you get negative E times the integral from A to B of dr. When you integrate all these dr's, you just get the distance d, right? So you get that the potential difference between the two plates is equal to negative E times, negative E being the electric field, times the displacement, or the distance separating. The separation distance of the capacitor plates, D. And notice it is negative, right? My final potential is smaller than my initial potential. That's why that negative is there. The electric field points down, the displacement's down, but the reason the potential difference is negative is the same reason that when you roll a ball downhill, it has lower elevation than it had at the beginning, right? So its final height minus its initial height is 0. Remember, make the analogy. A positive charge moving along electric field lines is like a ball rolling down a hill. Okay. So this is something that is not on the formula sheet that you probably want to just know for capacitors. The potential difference between them is just the negative of the electric field times the spacing. Okay. It'll be on the test. Okay. What? Negative ed. Yeah. Okay. So let's say we have this configuration here. And because he's never lost his power, Mr. Henderson comes along, says, you know what, I want to grab those capacitor plates and I want to pull them apart. Okay. Now, remember, we have positive charge up here, and we have negative charge down here. These plates are attracted to each other. They're being prevented, and let's just say they're being prevented by something. Let's say they put a brace here that's preventing these two guys from coming together because there is an attractive force. There is a Coulomb force. But Connor comes along and he wants to separate the plates. Okay. And so in separating the plates, he does this. Bad marker. And so let me draw the initial position of plate A. But then he stretches it so it's up here. And so originally, I had these electric field lines. These are my original ones. Before Mr. Henderson came over to shake things up. But now that he's separated the plates, there's more electric field now, right? There's these electric field lines that didn't exist before, but that now do exist. We're still assuming that the distance separating the plates is very small in comparison to the actual areal extent of the plates. And so we've created a new volume that is permeated by electric field, right? What did Connor have to do from a physics perspective to separate the plates? He had to do work. He had to exert a force on the plate, the top plate, to pull it up. And so his work translated into potential energy stored in the system. Just like when you lift a weight and lift this ball up from the countertop. I've given it gravitational potential energy. If I stretch a bowstring, I've given it elastic potential energy. If I pull these capacitor plates apart, I've stored some electrical type energy that we're going to talk about. And the electric field is still sigma over epsilon naught, right? Just like it is here. It's still the same. The electric field is still the same, but now it's filling more space, right? So you can think about field density, right? The field density is the same, but the total amount of field is actually bigger, but the strength of it, I'm getting ahead of myself. I'm sorry. Okay. Let's talk about how much work was done and its relation to how much energy is now stored. So when you do this, and I don't have the equipment here, but I will send out a link to Walter Lewin's lecture where he covers capacitance, where he actually has a capacitor plate that he can very carefully separate by just turning a dial, and you can actually measure the changes in the electric potential and the potential energy stored as he's separating the plates. But when Connor's doing the work in separating these plates, he's storing electrical energy in the system. And it is electrical potential energy, right? Because you can think if this system was free to move, if he pulls it up and then lets it go, it's just going to move right back because of the Coulomb force. Just like when you lift an object and let go of it, it just goes right back down because of the gravitational force. So, normally, I would go through how this equation gets derived, but because we have lost 4 days, and in this class, my Physics 1 class, I'm not too worried about because we kind of have plenty of time. They actually downgraded the number of units that we have this year. This class, I was already a little concerned about finishing by the end of the semester. So you're just going to take my word for it. In that same lecture, though, from Walter Lewin, he goes over it. But it can be shown that the electrical energy that we've now stored in this new volume can be written as an integral of the expression 1/2 epsilon naught, which obviously are constants, so they can come out, times the square of the electric field, integrating with respect to the volume, the new volume that we've created. This you're not going to need to know, but it leads to some very interesting results when it comes to storage, electrical storage.
It's just like a 1/2 mv squared. With electric.
Yeah, kind of. But this is the 1/2 mv squared comes from after integrating, right? This is actually before we integrate. The 1/2 comes from the fact that I'll send you a link to the video. You can watch the video if you want. Okay. Now the thing here, and this is what I'll finish on, because I don't think I'll have time to do much more. Thing that we want to note is that obviously 1/2 is a constant, epsilon naught is a constant, the electric field is a constant, right? So all that stuff can come out. I could have just written it like this to start with, but the process of setting this integral up, you essentially have du equals this, and then you just integrate both sides to get total energy U. So it's going to be that times the integral of dV. Where that's not potential. That's the volume differential. That's the infinitesimally small volume within this new macroscopic volume that was created when Connor separated the plates. And when I integrate all that, I just get the total volume there, right? And so, and note some equations that we already know. I know on my capacitor plates, the charge on the plate is equal to sigma times the area. I know the electric potential difference between the plates is the negative of the electric field times the distance, but I'm just going to talk about the magnitude of it for now, just to make my life a little bit easier. And then I can rewrite that equation as, I should have done the integral first. Let's do this integral first. 1/2 epsilon naught E squared times the volume. Can I do that? Look, I just did that integral. It was a hard integral.
Oh, yeah.
Is that Van de Graaff in your wafers?
How'd you do that so fast?
I'm real smart. My mom says I'm real smart. And so this is volume, that's not voltage, right? But what I can do is say, all right, well I have that volume, the volume here, the volume in this space, do another color, is the areal extent of the capacitor plate times my new separation distance. And let's call, I know I called this D over here, but let's say this is our new D. Right, we've extended a second distance. We can call this D1, D2. Call this D naught, and we'll just call that D. And so because I'm just focused on that new volume that has electric fields that didn't before?
Because length and width have height.
Yes, good. You remember.
Yes, I do. Wow.
So I can rewrite this as 1/2 epsilon. I mean, we need to use that. E squared times the volume, which is just going to be the area times that displacement d. And then we can say, all right, let's just make some substitutions. I can rewrite this guy. Area is charge divided by charge density. I can rewrite this guy as electric field is electric potential difference divided by distance, separation distance. That's what I'm trying to do here, right? Okay. And so I make those substitutions. I get 1/2 epsilon naught times the electric field squared, so that's going to be delta V squared over d squared times, doing this right, aren't I? Oh wait, let me do it like this. Let me do it like this. This is why I should read my notes before I do this.
I'll allow you to do this.
1/2. I'm only going to, and you'll see why in a second. I'm going to leave one e there, and then substitute in delta v over d for one of these. I'm allowed to do that, right?
If you say so. You can make
Why not?
as it goes.
I'm following the rules. I'm following the rules. And then that gets multiplied by the area, which I can substitute q over lambda. What did I do here? Yeah, sorry. For the area, I'm going to substitute in q. That's sigma, not lambda. Come on, Logan. It's not lambda. It's sigma.
Obviously.
And then times the displacement d. Sorry. And then, so notice that when I do that, d cancels. And I have Where's my Q still there? Q's still there.
The suspense is killing me, Mr. Green.
It does E simplified as sigma over epsilon naught.
Sigma over epsilon naught?
Or should
Oh,
we
yeah.
replace delta V with Q?
Well, we don't want to do that.
Oh.
Oh my gosh. I'll figure this out by tomorrow. Sorry.
Yeah, I don't know if I can take. Yeah, you could change out the E that's remaining into sigma epsilon naught, epsilon to sigma, epsilon to epsilon. What is the?
There. Yeah, Alex had it. You should have been teaching today. Sorry.
What did you say, Alex?
Yeah, what you said about replacing sigma.
Man, I was on a roll until that.
Because then that cancels.
I blame Gianni.
And the epsilon naught sigma.
You want to hear a joke that I just made up?
Okay.